Welcome back to Cosmos Unlocked. In Part 1, we have talked about the fundamental nature of antimatter, exploring its theoretical underpinnings and how its discovery changed the way we view particles and their interactions. Now, we take it further. In this second part, we'll explore some of the most fascinating questions about antimatter, from its mysterious existence in the universe to the scientific challenges of studying it. Let's uncover the secrets of how antimatter could shape the future of technology and our understanding of the cosmos. Because antiproton is also made of antiparticles. There's something even stranger. Once you have an antielectron, antiproton, and antineutron, you can further create an antiatom. An antielectron with a positive charge and an antiproton with a negative charge follow the same movement rules as their corresponding normal particles, except that their charges are reversed. If you get both an antielectron and an antiproton, the antielectron will revolve around the antiproton, and you will get an antihydrogen atom. This means that if you gather enough antiparticles together, you can create any form of antimatter. For instance, you can combine two antihydrogens and one antioxygen to make antiwater. The appearance, feel, and properties of ant water are almost indistinguishable from normal water, but if you drink it, you would explode immediately, because your body is made of normal water. So why can't we continue imagining? If you can create ant water, you could probably also create the opposite versions of any atoms and molecules. Perhaps you could even create anti-chemical compounds, anti-proteins, and anti-DNA. Maybe in another part of the universe, there's a planet made of antimatter, and perhaps there's a person who looks exactly like you, but is made of antimatter. This person might be driving an antimatter car, living in an antimatter house, and perhaps right now holding an antimatter phone while listening to this program. In fact, our matter does not have inherent materiality, and antimatter does not have inherent antimatterness. If the situation were reversed, and we had antiparticles, we would likely call our antiparticles matter and call normal particles antimatter, because it's all just our definition. In other words, maybe we ourselves are the anti-ones. Of course, no matter how much we let our imaginations soar, we must confront one question directly: where's all this antimatter? We know that antiparticles exist, and Dirac's equation describes their behavior at high speeds very well, but that doesn't mean we fully understand them. In fact, the strange phenomena of our universe raise more questions than answers. For instance, we've only observed a few particles, and that doesn't mean we can deduce all the properties of the matter they make up. Is antimatter the same as normal matter in terms of motion, texture, taste, color, and so on? Do antiparticles and particles behave the same under the influence of gravity, or is it the opposite? The biggest question is, why is our world made of matter and not antimatter? Looking at the situation we've observed, there's a huge, important, and very obvious difference between matter and antimatter. Matter is everywhere, while antimatter is almost invisible. This means that the amount of matter in our universe is far greater than the amount of antimatter. If matter and antimatter were equal, and each particle had a corresponding antiparticle, we would expect equal numbers of particles and antiparticles to have appeared in the Big Bang. Let's think about what would happen based on this idea. If every normal particle had a corresponding antiparticle, eventually, all particles would collide with their antiparticles and annihilate each other. All the matter in the universe would turn into photons. But since the universe we observe today isn't made up of only photons, we know that this is not the case. In other words, during the Big Bang, the appearance of matter must have far exceeded the appearance of antimatter. Now, there are two possible explanations for this inequality in current science, and I'll share them with you. The first possibility is that, during the Big Bang, there was slightly more matter than antimatter. The majority of matter and antimatter annihilated, but after the antimatter was used up, small amounts of matter were left behind, which became today's galaxies, stars, and even dark matter. You should know that dark matter is not the same thing as antimatter. This possibility does explain the situation we observe, but it is a bit of a lazy explanation, shifting the core question. It turns the question of why our universe is made of matter instead of antimatter into another question. Why was there more matter than antimatter at the start of the universe? That question also remains unanswered. Let's talk about the second explanation. In this explanation, there was an equal amount of matter and antimatter during the Big Bang, but over time, certain properties of these particles caused matter to be more prevalent than antimatter. If there is some physical mechanism that makes antimatter disappear faster than matter, or if the process of producing matter is faster than the process of producing antimatter, then this possibility is valid. Particles have continuously appeared and annihilated, and even if the process of their appearance and destruction differs slightly between particles and antiparticles, over time, this will create a huge imbalance. This second possibility seems more plausible, but how likely is it that the universe naturally tends to produce and preserve more matter than antimatter? In physics, broadly speaking, the laws are symmetrical. As far as we know, anything that a normal particle can do, an antiparticle can also do. For example, a neutron can decay into a proton, and an electron and an antineutrino can interact. Likewise, an antineutrino can decay into an antiproton, and an antielectron can interact with a neutrino. This second possibility might seem small, but when physicists study particles, they try to find subtle imbalances between matter and its antiparticles. Unfortunately, although there is evidence that this imbalance exists, we still cannot explain why there is such a huge difference in the amounts of matter and antimatter today. There must be something else that can explain this imbalance between matter and antimatter. This answer holds clues to another question: why were there two types of particles in the first place? But as of now, we don't know. We only know that charged particles have corresponding antiparticles because they have solutions in Dirac's equation. Physicists believe that neutrinos, which have no charge, may also have antiparticles. These antiparticles carry the opposite electric charge related to the weak force, which is called the hypercharge. However, because neutrinos are already a very mysterious type of particle, as we discussed in a previous episode, it is very difficult to capture them and conduct research on them. So, perhaps neutrinos are their own antiparticles. This is like what we said earlier, saying this is almost like saying nothing at all. Now, after all of this, how should we study antimatter? The idea of using antiparticles to construct antimatter objects is certainly very appealing. It's not only cool but also has significant implications. We can learn the differences between antimatter and normal matter, and it can help explain why antimatter exists. Unfortunately, experimenting with antimatter is extremely difficult. Even constructing objects with normal particles is already hard. For example, if you want to make a chocolate cake, you would need to control 10 to the power of 25 particles, and you don't need to worry about the cake exploding when it comes in contact with normal matter ions. Only recently, scientists succeeded in getting antiprotons and positrons to coexist peacefully in the laboratory and produce antihydrogen atoms. In 2010, scientists successfully produced hundreds of antihydrogen atoms and stored them for about 20 minutes. This was an impressive fundamental achievement, but it doesn't answer questions about antimatter. Imagine if you only had a little time to observe a few neutrinos, how much could you learn about antimatter? We've certainly made some achievements, but until we improve antimatter production and safe storage technology, we won't be able to deepen our understanding of antimatter. Currently, we can only produce a few picograms of antimatter at CERN each year. In other words, if we want to produce antimatter equivalent to the size of half a raisin, it would take millions of years. Even then, we would need to use electromagnetic fields to invent containers that don't require direct contact in order to store this antimatter resin. To summarize, we now know a few things about antimatter. We know that antimatter exists, and we also know that when antimatter collides with normal matter, they annihilate each other and release photons. We're not completely ignorant, but there's still much more we don't know. Firstly, we don't know why antimatter exists. Could this hold clues to the composition of matter? Are there other forms of matter? Matter and antimatter are symmetric, but our universe clearly favors matter. There are still many unanswered questions about antimatter, such as, do antiprotons behave like normal particles when affected by gravity? We know antimatter exists, and current theories predict that it would behave like regular matter in terms of gravity, but since we haven't observed enough antimatter, we can't answer this basic question yet. Gravity, also known as gravitational force, is a rather weak force, and we can only measure its effect when we have a large number of particles. But antimatter is rare and unstable. But what if antimatter behaves differently in terms of gravity? Remember, the key characteristics of antiparticles in electromagnetic force, weak nuclear force, and strong nuclear force are that their electric charges are opposite to those of normal particles. If this is true, and we find a way to use this anti-gravity property, what might happen? Perhaps the flying cars and anti-gravity boots that people dream of could be made. Earlier in this episode, we talked about dark matter and dark energy, and today we discussed antimatter. If you've confused their concepts, you can go back and listen to our explanations of dark matter and dark energy. Finally, I want to say that in science, new concepts often arise. When we first hear them, it may seem like physicists just made them up out of thin air and then science fiction writers incorporated them into their stories. In fact, it's not like that. It's not that scientists make up a concept and then use it to solve a problem. Instead, they first find a solution in mathematics, and then create a term to name that solution. So, for issues related to economics or sociology, ordinary people can freely express their opinions. But when it comes to physics, it's best if ordinary people don't argue. If someone really wants to communicate with physicists, it's better to first grasp the necessary mathematical knowledge before having meaningful conversations with them. For most ordinary people, we're just here for the entertainment, to expand our minds, and that's enough. Alright, that's it for today's episode about antimatter. Feel free to leave me comments, and we'll see you in the next episode.